I leave the things there.
Just one question. Quem não ensinou a mim, nós vamos sortear um livro. Onde você testa para ele? Per colpa tua, per me non siete.
Bisogna soffrire nella vita. So, I have the honor to be the last lecturer of this anniversary edition of the school. So, I would like to thank Mario in the name of everyone who is present for having organized once more the school. So, since it's the last, this is the last lecture, I have quite an amount of material to show you, but I will run through my presentation just for you, to let you know that these things exist. At least if you are interested in the sitter, you should not overlook these things, but I will go a little bit fast. But first, I want to answer better to a question that was posed yesterday about the commutator. So let me resume where I stopped yesterday concerning quantum field theory on curved space-time. A quantum field is a singular object. It does not exist as a point-like object, but just as a distribution. And if you are interested in free fields and you have a Lagrangian, one thing that you can construct in a unique way is the commutator of the quantum field, and this commutator has two, the requirement for scalar fields or for bosonic fields. The only thing, if you are on a globally hyperbolic manifold, the only requirement that you have to impose is that it is zero for space-like separated event. So the question is, how do you construct the commutator? Canonical quantization is about constructing the commutator. So here is what a globally hyperbolic manifold is. So it can be foliated by space-like hypersurfaces, Cauchy complete Cauchy hypersurfaces, and you can identify a time variable. So these are unnecessarily complicated, this expression, but I wrote the correct ones. For a scalar field, you have a Lagrangian, and you derive the equation of motion, as I told you yesterday. And the equation of motion gives to you uniquely the commutator. How? You can associate to your equation of motion a unique, let's say, symplectic form whose correct name is Peierls symplectic form, even if it is everywhere quoted as the Klein-Gordon scalar product. So you have this. I wrote here in an imprecise way. Here it is the precise definition, but it's nothing but you need the solution to be complex on the other hand. So the phase space is the space of complex solution on the Klein-Gordon equation. And then, if you are able to find a basis in the space of complex solution of the Klein-Gordon equation in your manifold, which satisfy this condition, you can diagonalize the commutator, and this expression is unique in the sense that if you find a second family of solution satisfying the same condition, and you write the same expression in terms of the new family of solution, the second one that you have, you get the same commutator. So this answer is completely fixed by the equation of motion. On the other hand, if you now want to quantize your theory, what does it mean quantizing a theory? It means constructing a Hilbert space where you represent your field operators. Then you have to look for a two-point function which is going to be interpreted as the, let's say, vacuum, but this is a reference state, let's say a cyclic state, where so this distribution is going to be interpreted as the two-point vacuum expectation value, and it has the following relation with the commutator. So W of xy minus W of yx equal to the commutator. This is a functional equation, a non-differential equation. It has infinitely many solutions, even in flat space. So you need a physical insight that, if any, if there is one, to choose among the many possible solutions to this equation, the one which represents the physics that you want. You see, so in this sense, the Lagrangian does not tell you what the physical space is. The Lagrangian only tells you the commutator. There is not enough information in the Lagrangian. So one way, the standard way to produce this kind of information is to relate the physical property you want to encode, like positivity of the energy, like thermal spectrum, into analyticity properties of the correlation function in a complex extension of your manifold. So this is the way, for instance, the vacuum, the standard vacuum representation of quantum field theory in flat space works, and in the same is true for the thermal representation of quantum field theory. The same is true for the, let's say, quantum field that you construct in Schwarzschild space to describe the Hawking radiation, and all the known examples are in this way. So let's go back to the sitter. So, and apply this idea to the construction of a basis of solution of the Klein-Gordon equation. So, as I showed you yesterday, several coordinate systems, but you don't need to use any of them to solve the Klein-Gordon equation in the sitter manifold because of its maximal symmetry. So if you think to the de Sitter manifold as a complex sphere, you can build these functions. You see, x is a point on the de Sitter space-time, real or complex. Xi is a vector on the light cone in the ambient space. So you construct the scalar product in the ambient space sense, and you take a complex exponent. This function is going to be the analogous of the plane waves of flat space-time, in which you take out the mass here. So you take just the momentum direction here. Lambda is going to play the role of the mass. Xi is going to play the role of momentum direction. So if you do this, you can make the exercise home that these functions solve the Klein-Gordon equation on the de Sitter manifold, d-dimensional de Sitter manifold, relative to this eigenvalue. And you see there is a symmetry in the eigenvalue. If you send lambda into lambda bar, which is minus lambda minus d minus 1, the eigenvalue stays the same. So you have these two solutions, xi lambda bar, solve the same equation. So they have a complex value of the mass square. This is important to have this complex mass square. For instance, when you want to solve for spinor, you need complex masses. So there are three families of solution for scalar fields. This is the so-called principal family of de Sitter waves. You see, lambda is a complex number, but for this choice of complex number, the square mass is this. By the way, if you put a radius into the de Sitter not take the radius equal 1 as I did here, but you put the radius equal to r, you have to divide this nu by this nu by r. Or you multiply this nu by r or divide this thing by r. So there is a dimension there. But don't for the moment I don't care of this in this moment. So this family has a minimal value of the mass, and this family you see the involution lambda into lambda bar is just a complex conjugation. So this family of waves is are the waves which are really close to the exponential of the flat space. There is a second family of waves in which this number now is real. Before, it was purely imaginary. Now it's real. And because it is real, now the mass takes these values in between this maximal value now and 0. This is called the complementary family. These names come from group theory. And you see that these waves do not oscillate. They are real waves. So these are low masses field, including the limiting 0 mass field, which is so important in the context of inflation. And they are completely different from flat space wave, and you see that they are not real, they are not oscillating waves. This relation is no more the complex conjugation. So they are tricky things, and all the issue about instability that was mentioned before concern this part of the spectrum. But I mean, these are really, there is no intuition available here. They are completely counterintuitive. And there is even a third family of waves when this mass square takes negative values. This possibility, which is forbidden in flat space, which is forbidden apart from a small part of the spectrum in anti-de Sitter case, is completely open in the de Sitter case because the energy operator has no lower bound. So you have the possibility to consider this, also this part of the spectrum, and in particular there is a privileged family of this kind of tachyonic waves. I call these tachyonic waves just because they have negative square mass, but I will show you in a few minutes that there is no problem, at least for those integer mass waves. So the problem is that these waves, since you take the complex exponent here, are singular. There are places in which this argument, this phase vanishes, so you don't know how to glue together the portion of the de Sitter universe where this thing is positive with the one where this thing is negative. So you need a prescription, a choice of these two coefficients. The choice of these two coefficients will amount to the choice of vacuum. So here comes the analyticity property I was mentioning. So you move to the complex manifold, you put an imaginary part to your de Sitter point, but you keep the equation. So the equation remains real. So the real and the imaginary part have to be orthogonal in the ambient space sense. So you have a future pointing tube and a backward point tube. These tubes are the analogous of the tubes in flat space, which represent the positivity of the energy. So if you do this, now there is no more problem in both these two domains to define global waves. Okay, there is no more ambiguity, and you can even take the boundary value in the distribution sense, and the boundary value fix for you the choice of the coefficients. So here are the choice. I won't say the correct choice. I would say the choice imposed by the analyticity domain, which are the corresponding to the positivity of energy in flat space. You cannot formulate positivity of the energy here, but you can keep the mathematical property, which they do have. I will tell a few words about the physical interpretation of this choice, which is one which you know very well. So to make contact, which may be things we are more used for, you can take this plane wave and try to represent it in coordinate systems. So you choose, for instance, the coordinate system of flat sections of the De Sitter manifold. This is the choice of the coordinates on this portion of the manifold. And this is the corresponding choice on the tube. So you have to parameterize both the point and the momentum variable. So this is the parameterization of the momentum variable in terms of one vector, a space-like vector, and this is the usual coordinate system used in inflation. And then you make the space Fourier transform of these plane waves with respect to the x variable. And you get the function of eta, and then you see what you get here, just the Hankel function that arises in the Bunch-Davis vacuum. This is corresponding to, H2 is corresponding to the forward tubes. So the analyticity property I was saying are exactly encoded in the Bunch-Davis choice. But this is not the only possible choice. So this is the other one. The backward tubes, you get H1. So in coordinates, these very simple objects, of course, have involved expression in terms of special functions. But you recognize things you can read in papers and books. In the, which is, for me, this is, indeed, this is more important in the global coordinate system. So this is the global coordinate system. Now you parameterize the light cone just with one vector normalized to 1. Then you make the transform in spherical harmonics of these plane waves, and you get the right choice of the Ferrer's functions, which are also called Legendre functions on the cut, depending on this choice of variable, a purely imaginary hyperbolic sign of the time variable. This is automatically encoded in the analyticity properties I was describing. So, and then you can give a Fourier representation to the two-point function, which is closely similar to the one you are used to in flat space. This is the Fourier representation of the two-point function of a Klein-Gordon field of mass m. You see two waves, one which is holomorphic in the backward tubes, the other which is holomorphic in the forward tube, and the mass shell. Here the mass shell is the choice of lambda, and the holomorphy, this is the backward tube, and this is the forward tube, and you integrate this psi variable over this basis or over this basis, depending on what you prefer. So this is completely covariant expression of the two-point functions of the Klein-Gordon fields, even for complex masses on the De Sitter manifold, and it produces all, in this formula there are encoded all the special functions that you can need. Hankel functions, Legendre functions, they are all there. So, and then you can use the De Sitter invariance and show that indeed this expression is not only analytic in this domain of the complex De Sitter manifold, but indeed there is a cut plane as in flat space, and just this is, so this is the two-point function is a Legendre function. This is also, of course, known in books, but this Fourier representation is in one paper of mine, is not very used. I mean, but if you want to do hard calculation, you cannot avoid to use this. I will show you an example. You get a maximal analytic two-point function, which is analytic in a cut plane of the invariant variable. The scalar product is in the ambient space sense, and the cut reflects causality. What is the physical interpretation? If you now plot, if you now express this analyticity property using the coordinate system I was showing you yesterday, which was introduced by de Sitter himself, in which you do have a time translation invariance with respect to this time t, which is related to the one parameter subgroup of the de Sitter group, then you see that this is an automorphism of this region, and the maximal analyticity property, which we were mentioning in the invariant variable, become in this t variable a strip, and you get periodicity on these boundaries, which is and these two conditions are known under the name of the KMS condition at T inverse temperature T. So this is the famous de Sitter temperature. When you hear someone telling you that there is a temperature in the de Sitter universe, don't believe him, because he's wrong. What is true is that when you restrict the field algebra to this region of the de Sitter universe, and you look to your correlation function in this time variable, then you see a temperature. This is the correct way of saying things. So, this part is for I put these two slides for Cedric, because if you look at this two-point function, go back and look. So there is this. So here in the two-point function, you see the coefficient has a gamma of minus lambda here. So when lambda is an integer, this constant diverges. And when lambda is an integer, this becomes a polynomial. So what happens when lambda is an integer, as I told you, the two-point function goes to infinity, but it goes to infinity in a trivial way, in the sense that what it goes to infinity is the constant in phase of the two-point function, while this thing becomes a polynomial. But a polynomial, from the point of view of quantum field theory, is completely not interesting, because a polynomial is an holomorphic function. There is no cut, so there is no there is nowhere the field are non-commuting variable. They commute everywhere. There is no quantum feature in a holomorphic function, you see? So you need the cut. On the other hand, if you take the limit of the commutators, there is no problem. The commutator is perfectly regular if you go to lambda to n. This is a local function in the sense that it is these fields commute a space-like separation. So you might think that there exists a quantum field theory for lambda equal n, and I say you once more, lambda equal n is a tachyon. The square mass is negative. So what happens? Okay, I cannot now explain all the details. So this is the commutator. You can do an infrared renormalization in the same way you do when you use bidimensional massless fields. And what happens is that, indeed, there is a limit, but you are introducing an anomaly in your fields equation. Your fields equation do not solve anymore Klein-Gordon equation with this negative mass equals 0, but Klein-Gordon equation with this negative mass equal a charge. If you impose vanishing of this charge on the physical states, you get a huge infinite dimensional physical space. So this is the analogous of the Gupta-Bloiler or BRST quantization of gauge theories. And indeed, under these theories, having negative integer masses, there is a gauge symmetry in which, so you quantize the theory in a de Sitter invariant way. So these are de Sitter invariant local covariant quantum fields having negative masses. The gauge symmetry is finite dimensional. In the simplest case, is the same as the massless Ebony mass is phi plus constant, and then it's a finite dimensional gauge transformation. But in the n equal -1 case is related to the Hilling symmetry. This is a work I made in collaboration with Henry Epstein. So there are, if you are interested in any mass, any negative square mass, you can still quantize the theory, but you have to break part of the De Sitter invariance.
The vacuum changes, no? If you have the tachyon.
What?
The vacuum changes if you have the tachyon.
No, there is. I am just saying the contrary, because the negative can be, the energy can be as negative as you wish here. That's why you can have these things. This disappears in the flat limit, of course. If you take the flat limit, everything shrinks to 0.
Totally agree.
Okay. But that's why I'm telling you that the sitter is not intuitive at all. Okay. So let me show, if you want to make a hard computation using this thing, you can consider, how much time do I have yet? 25 minutes, okay. So you want to compute the life, a decay of particles. So I skip all the details. And so if you compute this amplitude, you can get lifetime of your particles as the inverse of the amplitude. This is the flat space result, which is the easiest computation you can do in quantum field theory in flat space-time, even if there is something wrong in this computation, since one state is not asymptotic, but the result is correct. But of course, there is the Fermi renormalization behind it. But still, if you want to do this, so I consider here this trilinear interaction between these three scalar fields and consider the same process of one particle to be destroyed and create these two particles. Let me use the word particle, even if we know that this is a dangerous word. But words are always dangerous, as you know. So you have to compute this expression. So you put a space-time dependent coupling constant here. This is the 0 field. This is 1 field. This is a 2 field. You have to compute this amplitude. So to compute this amplitude, you need to compute something which is called the Cullen-Lehman weight. And here, I showed you before that the two-point function is a Legendre function. You need to compute this integral. It's the product of three Legendre functions. And if you are able to compute this integral, then use this formula. This gives to you the Cullen-Lehman weight, which enters in the calculation of this lifetime. So first thing what you do, you go and pick the Gradstein-Ridgick in your library, and you don't find this formula. This formula is not there. At the end of a long search, you find a formula which is similar to this in one particular case in the Prudnikov book. I don't know if you ever had this Russian 5-volume book in your laboratory. Now the guy who wrote this book worked for Wolfram. And I wrote to him because I used this formula to compute the case of two equal masses in 2 dimensions. And but there is something strange in this formula. And he answered to me, yes, I know, this formula is wrong. It will disappear from the next edition. I tell you this, so you never trust a formula you read in one of these books. Always verify.
So Mathematica could be wrong.
That particular formula was wrong. I think now it's not more in Mathematica, probably. But I can tell you what is the formula in the Prudnikov book.
A checkmate.
Okay. So, by the way, this formula does not exist, and I computed this integral not alone, in collaboration with Henri Epstein and Michel Godin, Jacques Barros, and Vincent Pasquier, and this is the calculation I'm most proud of in my life. It took me 5 years, but I did not work every day to this problem. Simply, I did not know what to do. In the end, so you are used to use Mellin techniques to compute Feynman integrals, but here Mellin techniques do not work because you need the analogous of a full Fourier transform. So what you go back to the representation I gave to you before, And you compute in the deep analyticity region. So you go deep in the tubes, you put purely imaginary points, and you put on this sphere. These are the choices. In the end, you get this. Okay. In the end, you get this new representation for this thing which is entering in the integral we want to compute. In terms of imaginary plane waves, the waves I showed to you before. So you do this, and then you are able to transform this integral, which is a one-dimensional integral, in a convolution on these spheres times this hyperbolic Lobachevsky space of these waves, you see? You integrate all the variables here. Psi belongs to the sphere. What is the sphere? The sphere is the spherical section of the cone, so it's the momenta. You integrate so, and this point, this is the de Sitter manifold in the analytic continuation. So I have to integrate all these points here. We transform this one-dimensional integral into this one. And this is advantageous because now you can compute it. First, you can compute easily the integral over y. You just need to compute this constant because of invariance. So this is so-called a star triangle transformation. And second, you have to compute the triangle. This is more difficult. Indeed, you see that here, I don't enter in any detail, of course, here. But if you want, I can explain all the details. In the end, you get a probability distribution. So this integral corresponds to the probability of drawing a triangle on a sphere. What is the probability that the angle are such and such? And in the end, after all of this, so it's a probability distribution because this function integrates to 1. Here is the result. So the integral of these 3 Legendre functions is the ratio of these 8 gamma functions over the product of 6 gamma functions here. So I find this formula extremely beautiful because it's my own, but I don't ask you to have the same feeling, but you can still have it. And the crucial point of this formula, the crucial difference with respect to flat space, is that this formula never vanishes. In flat space, you get theta functions. And the theta functions tells you that a particle of mass m cannot decay into 2 particles having whose sum of masses is bigger. Here it can happen. 1 particle of mass m can decay into 2 particles of mass m1 and m2, irrespective of the 3 values of these masses. This could seem to point toward a certain instability, as we were told before, of the de Sitter space, since this is a disaster from the point of view of quantum physics, because particle keeps decaying if you put interactions. But of course, this is not so obvious. That apart from the fact that with the present value of the cosmological constant, it will take more than the life of the universe to see this phenomenon. So this is also in. Excuse me? D is the dimension of space-time, any dimension. And by the way, one thing I have to say that this formula is very easy to be computed directly in odd space-time dimension. Because in odd space-time dimension, these functions are hyperbolic sines and cosines. In even space-time dimension, this is the result. There is no direct way to compute it. You have to go all this path. So here is the shape in the dimension d equal 3, you see. This in the dimension d equal 3, this is easy to write for 2 particles having equal masses, you see. It never vanishes. And it goes to the theta function when you take the flat limit. So, But in the complementary part of the spectrum, so for low masses, the situation may be right the opposite. Even if you put an interaction, things do not decay. But this is a very difficult problem. Make computation of quantum field theory on the de Sitter spacetime for theories having small masses, even if covariant, I mean, from 0 to d minus 1 over 2. So this is so difficult that I don't have a final answer to this question. The previous result was just for masses bigger than d minus 1 over 2. So, so this is the movie. One particle can decay into two other particles. So let me now abandon this thing, and I wanted to go to the last thing. So there are very interesting things found in the complementary part for low masses. For instance, if you look really at your two-point function, but you don't look only to the two-point function, but you go and look in the in the two-particle, in the three-particle, in the four-particle sectors of your Fock space, there are bound states that are possible now if the mass is small. And these bound states can cooperate against this phenomenon. So the question of stability is really tricky. So let me just, so these are perturbative phenomena. So you may ask yourself, maybe these are artifacts of perturbation theory. What happens if you move to non-perturbative quantum field theory? And as you know, there are two non-perturbative things in quantum field theory. One is lattice models, and the second is two main, let's say, solvable models. So I tried to see if the models which are solvable in flat space remain solvable in the curved space context, and if yes, what we can learn from the study of these models. So I studied, for the moment, the Turing model. In the end, we were able to solve it. So I skip all the details and then just go to the last. But I can tell you, for those of you who are in Rio and maybe are interested in this thing, I will be here for 2 weeks, so I'm available to discuss the details of what I'm not saying today. So I don't tell you anything about this, but just want to go to the surprise. The surprise is the following. Since in 2 dimensions the topology of the de Sitter manifold is non-trivial, you can cover the spatial dimension, the de Sitter manifold. So in the end, what we learned in studying this theory with Henry Epstein, so don't look at this, that you can solve. So there are two. The point is that if you open a book in string theory in the first chapter, you learn that there are two family of spinors. One is called Ramond spinors, and the other is called Neveu-Schwarz spinors. The first spinors are periodic on a cylinder, and the second are anti-periodic. So the Neveu-Schwarz spinors do not live on the cylinder itself, but on the double covering of the cylinder. This is known also in conformal field theory, that conformal symmetry is preserved by the Neveu-Schwarz spinors and not by the Ramond spinors. The same is true here. After opening the book, trying to solve, following the recipe that you read in books, and having failed, in the end, we understood that we can solve the Turing model moving to the double covering of the two-dimensional de Sitter manifold. So why I'm telling you this? So I don't want to enter in this detail. Then you can. So what is the double covering? If you let me just make one picture here. But on its double cover. Just a simple equation. Can you use this one? Okay. Just a simple equation. Try. It is extremely interesting. You will see that this when you write the commutator in one case. Let me just write this. Can you just lift a little bit this? When you write the commutator in one case, you get an expression like this. P minus L. These P are the function that you saw before. Minus the one in which you interchange these two things. So in the de Sitter case, the sum is over the integers. In the double covering, the sum is just over the integers and the alpha integers. So you double in a certain sense the sum, but you divide by 2. So these two commutators are identical locally, but they are different globally. Means that this commutator in which you sum over the integers does not vanish here, but the commutator in which you sum over the integer and the alpha integer is identical here and vanishes here. What is the consequence of this seemingly mathematical result? Is the following. Now, this is the double covering, so you have to think of this manifold that you make a full round trip. Then you end up in the second one, make a full round trip, and you come back in the first. Okay? So you try to solve the Klein-Gordon equation according to the locality of this manifold, which is different from the locality of the true de Sitter universe in the sense of this figure. The first commutator, the de Sitter commutator, let's say, is not zero here and here, and the commutator on the double covering is non-zero just here. Here they are identical, here they are different. I have an exact solution for this problem, and then you try to solve. So this is perfectly de Sitter invariant, but now the de Sitter group is no more SO12, but now it's SL2R. It's the double covering of this group. So what happens? Now take the commutator of the covering C of X and Y on this manifold here, and try to solve for these 2-point functions. Then I found all the solution to this problem, and the surprise is that now, even if locally, there is no difference. So if you look around the point, you can believe to be on the de Sitter manifold. You see two horizons, exactly as in the de Sitter case, but there is no invariant pure state, and the Hawking temperature disappear. So this is a counterexample to the belief that when you have a bifurcate killing horizon, you have the Hawking temperature. Here, you won't find any Hawking temperature because of a topological difference. So, if you have your de Sitter universe and you take away one line, the physics can change dramatically. And I think I'll stop here.
You saw in the last lecture the instability of the Sitter space in quantum scalar field, right? Here you have the same thing. Where I can see the instability here in your language.
It's not so obvious from, because I mean, in this part of the spectrum where it should be, for massless or little mass theory, the theory is so involved. I don't have any answer. I mean, my result for decays of the Sitter particles in the principal series do not apply in the I have also result which I don't believe very much, which I published with Akhmedov concerning some sort of infrared in this part of the spectrum of the theory, but we don't have any result on the lower part of the spectrum of the theory because it's really complicated.
So before I ask a question, is there anyone else who wants to ask a question? Because I'm going to ask a very difficult question, Hugo. So I think actually I would like to ask the question to Mario. So I think on behalf of all of the attendees, I think I would like to thank you for taking the lead of organizing all of these schools over the past many years. And thank you for all of the efforts that you've made. And I wish you good luck in organizing future schools. So let's thank Mario and all the other organizers.
Let me just add one thing. This is obviously not a one-man job. We have a lot of people behind us and also companions. And now we have the new generation, as you see, for instance, Nelson Pinto and Martin Makler, which is not here, Sergio Jorais, and all these people, which will do this job, I hope, in the future. And perhaps the next one I will be here also, but in any case, they will continue this job. I hope this. You have comment anything else?
No.
Oh, I have two comments. So I would like to thank you, Hugo, first of all. Second, for the people which speaks Portuguese, I have this book, which I just publish it, and I'll make, I do myself because there's no problem like this. But I see. Number five is. Number 5, Heitor da Silva is here, so please. Okay, so this is the end of the school. I thank you, Roberto, for this, and thank all people from here. Cedric, which is still here. Pão de Açúcar is just there, waiting for you. Roland Trier, and don't remember, this school was dedicated to the memory of Professor Edgar Lebas. I'm sending up a small, how do you say this, plaqueta in English? To him, that I hope Roland could send to his wife. Okay, well, thank you until the next one. Just one final comment for the Brazilian students. I don't know if everybody knows this exercise of cosmology, which is for free. It means, and there is a new translation in English, which will appear this year. It's still free, which contains 500 exercises in cosmology. It is free in this in my site marionovella.com.br. Okay. Okay. Thank you. See you later.